Hey, I know some of you didn't get to see the end of the last video I sent because maybe it was too long and you were not patient enough to watch it through. But at the very end of the video, I gave you the homework assignment. So make sure you go back and fast forward it to the very end if you need to, and make sure you get the homework assignment from that AP packet. And in this video, I just wanted to address a couple of things. And one of them is the many different ways they can ask the same question. So we have a function defined by an integral, s of m, which equals the integral from -2 to m of the ln of 2 minus x with respect to x. And again, for this example, the x variable is actually your standby or the dummy variable, and the main variable is m because s depends on m. And so these are 5 different ways that they could ask the same question. If they say find the rate of change of s with respect to m, that's exactly the same as saying find the derivative of s of m with respect to m, or simply ds dm. Another way would be find s prime of m. One more way, find the instantaneous rate of change. And another, find the derivative of s of m. Notice the first and the second to the last, rate of change of s or instantaneous rate of change of s. Why are they the same if one of them just says rate of change and the other says instantaneous? Well, as long as it doesn't say the average rate of change, then it's understood to be the instantaneous rate of change. So if they say rate of change, that's exactly the same as instantaneous rate of change. And this is the derivative. If they wanted the average rate of change, they have to specify by saying the word average. And if it doesn't say average, then it is the derivative. And please understand that's an important difference. So rate of change and instantaneous rate of change, it's basically the same thing. What about the average rate of change? That would be the slope of the secant line, and for that's just the algebra equation of slope. So you would do f of x of 2 minus f of x sub 1 over x sub 2 minus x sub 1, or whatever function they gave you. But if they say rate of change or instantaneous rate of change, it simply means the derivative. So then all these 5 different ways, they basically have the same answer. And to find the derivative of the integral, I am just going to use the theorem. And the theorem says that I should get the integrand ln 2 minus, instead of x, my variable, which is my upper limit, m. Okay? And that is it. That's the answer for the first question, the second question, the third question, the fourth, and the fifth. They all have the same answer because they are basically the same question. Okay? Now, the only difference would be if they said something like, let me just go to the first one, and let's say the first one said something like, find the rate of change of s with respect to m, and now I'm going to add at the point where m is equal to, and I'm just going to make up a number, like half. Then you can attach this to the rest of the four other questions. It'd be the same thing. So what do you do there? Well, you still do ln of 2 minus m, but then at the end you evaluate it. So then you would say that's the ln of 2 minus a half. So first take the derivative, and then after you take the derivative, evaluate or plug in the value. So we could say that s prime at 1/2 is equal to this. Okay? So first s prime and then plug in the 1/2. To find s prime, use the theorem, and to find at the value that they gave you, then just plug in the value. Alright. Here's another very common question. This one goes back to the average value. Now, this is not an average rate of change, it's an average value. And so they're saying you have a function x squared minus k, and the average value of this function from 0 to 1 is 1/7, and they want you to find the k value so that the rest of it is a true statement. So we have to go back and think about what do they mean by average value, and we had an equation for it. The equation for average value is, hopefully you remember this, 1 over b minus a times the integral from a to b of whatever function you want the average of. They want the average value of f, so my integrand has f of x dx. And what they're saying is that this average value has to be equal to 1/7, right? So then, and it's over the interval 0 to 1, so there's your a, there's your b value, and all you have to do is plug it in, set up an equation, and solve for the equation. So then that would be 1 over b, which is 1, minus a, 0, times the integral from 0 to 1 of f, which is x squared minus k with respect to x, and this average value has to be 1/7. And now I performed the operation, the integral, and solve for k. So then this would just be 1 over 1, right? And the integral is x cubed over 3 minus the integral of k is not 0 because this is not the derivative but the antiderivative, so kx, and I'm evaluating from 0 to 1, and at the end I should get 1/7. And if I evaluate, I'm gonna ignore the 1 at the beginning there, so it'll be 1/3 minus k times 1 is k. That's the upper limit, minus, when you plug in the 0, you're going to get 0 minus 0, and that is 1/7. And so now we have that 1 over 3 minus the k value is equal to 1/7. I'm going to move the k to the other side, and then I'm going to displace the 1/7 to the other side. And there's my k value. And I guess I'm going to need a common denominator. That would be 21, so times 7 here, times 3 on this side, and that's 7/21s minus 3 over 21, and so k would equal, what's that, 4 over 21. And it doesn't have to be a nice number, it's just some constant k. There's quite a few questions like this on that AP packet, maybe 3 of them. And so all you have to do is follow the formula, make sure you've memorized the average value, and be very careful with your algebra as you solve the equation. and as you evaluate the upper and lower limits. And that's it for that. And the last example for this video, I have a function and a graph. Now, the graph is labeled as the graph of f, and then I have another function g of x, and g of x is equal to the integral from a to x of f of t dt. And the question is, find the relative extrema of g of x. So remember, the graph is not the graph of g of x, it's the graph of f. But f and g are related by this integral. So to find the relative extrema, I'm going to do the same thing we've been doing all along, which is, let's find the critical values for g of x. How do you find critical values? You take the derivative of the function whose maximum and minimum you're looking for, so g prime of x, and you set that equal to 0 to find critical values. But what is the derivative of it? Well, because g of x is given as the antiderivative, then by the fundamental theorem, g prime of x should be equal to, take a guess, f of x. And so this graph, which is the graph of f, now we can come back and relabel it. This is also the graph of g prime, because g prime of x is equal to f of x. And this is a very important statement to make. So then, if I want to set g prime of x equal to 0, that means let f of x be equal to 0, okay? So g prime of x equal to 0 means that f of x is also equal to 0. And where does that happen? Oops, I forgot to label some numbers. So let me just do that real quick. Let me call this point C, D, E. Alright, so then g prime of x is equal to 0 when x is equal to C and D and E. And those right there, those are critical values. And what else do we need? We need endpoints to, oh no, we don't need endpoints, we just want the relative extrema. So then out of C, D, and E, we should be able to find relative extrema. What would you say happens at C? Is C going to give us a relative max or a relative min? Well, at C, g prime, which is the same as f, is changing from negative to positive. So from negative slopes to positive slopes. Wouldn't you call that a minimum? So g attains a relative min at x equals c. Now, does that happen at D also? No, but it happens again at E. It changes, G prime changes from negative to positive. So that would be one other location. So G attains a relative minimum at x equals C and x equals E. And we need a complete statement because, and this is where you have to make the connection again, G prime, which is equal to F, changes from negative to positive at x equals C and x equals E, or you can just say at those points. So there we found the relative minimum or the relative minima. And now for the relative maximum, it should be clear to you now that it happens at x equal to D. So we could also write that down. G attains a relative max at x equal to E because G prime of x, which equals f of x, you want to make that clear to the person who is grading your test, changes from positive to negative at that point. And there we answered the relative extrema question. So what now if the question is find the absolute extrema? And let's assume that I know nothing about the relative. So assume that we didn't have any of the analysis that we did just now. So this is a brand new question. Find the absolute extrema. And it's the same graph. And so then I would start by saying that F attains, oh, no, I'm sorry, not F, but G. G attains relative extrema at x equals C, D, and E. And I'm not going to go into details trying to tell them if they're relative maxima or minima. I'm just going to say they're relative extrema because G prime of x, which is equal to f of x, changes signs at those points. And that's what makes a relative extrema, whether it's a maximum or minimum. Changes signs at those points. But I do have to establish the fact that these are relative extrema. Now the question is, what are the absolute extrema? So then what we have to do is between the absolute extrema is going to be either one of the critical values or one of the endpoints. Okay, so then we have to test endpoints and critical values. And the way to test them, in the past we would just say evaluate the function, right? So if you have 3 critical values and you have the endpoints, then plug in the numbers into the original function and then the primary, which is g of x, and we would just get the number a, plug in for x, c, plug in, d, plug in, e, and b. But then the problem is that none of those are actual numbers. The graph, I mean, this is how they're going to give you the graph, a, c, d, e, b. So if they're not actual numbers, then we cannot get a solid number to compare them to each other and then say this is the absolute maximum, this is the absolute minimum. But there's a way around it, so we can still figure out the max or min, and the key is going to be thinking of areas to find the integral values. Okay, so this is what I'm going to do. I'm going to compare the critical values against each other and the endpoints against the critical values and each other until I get something that tells me this must be the maximum, that must be a minimum. And so this is how the process begins. I'm going to label this, I'm going to label this absolute max. And if I'm looking for the absolute max, then I should start by saying which one is the relative max. The relative max happened at D, remember? So again, I'm pretending that I didn't have the information from before, so I kind of have to rewrite it now. So I'm going to say G attains, this is very repetitive, but it's the way it has to be. G attains a relative max at x equals D because G prime of x, which is equal to f of x, changes, I know, very repetitive, changes from positive to negative at x equals d. And that would be the only relative max. So then what I have to do is compare that to not to C or E anymore, because C and E are relative minima. I just have to compare x equal to d to my endpoints A and B and see which one would give me the greatest value, because I'm looking for the absolute max. So then what we do next is compare them. Okay? So I'm going to find g of, let me start with my endpoint A. G of A. I'm trying to compare my endpoint to my critical value and then back to my other endpoint. So then remember, g of x is over here. So when we say g of A, that means let x be A. And so when I rewrite the other side, my x, which was my upper limit, now becomes A, because x is A. Okay? So it'll be the integral from A to A of f of t dt. And you've seen this before. The integral from A to A would be 0, because there's no space given to accumulate any area. And so now I'm going to do g of d, which was my relative maximum, because I want to see if this would give me a greater value. And again, the question is, how do you know if it's going to give you a greater value if d is not an actual number that you can plug in and get a number out of? Well, this is how it's going to happen. We're going to take the integral from a, because that was the lower limit. I can't change that. X is d now, f of t dt. But then what do you know about this integral from a to d? Well, looking at it, from a to d, I have this area, which is below the x-axis, but then I'm going all the way to d. Then I have this area, and wouldn't you say that we have more area above the x-axis than below the x-axis? So then what I can say, even though I don't know the actual value of g of d, I know that this is positive. Okay? And that makes g of d greater than g of a. So can you see that if you compare these two? Because g of a was exactly 0. There was no area for g of a. But g of d accumulated some positive area. So then I can make a statement here that g of d is greater than g of a. Remember, we're looking for the absolute maximum. So at this point, my critical value, which is g of d, gives me a greater value than my first endpoint, which is a, and the value g of a. Now I only have to compare my last endpoint, because the absolute maximum could happen at the endpoints or at the relative maximum. And so we'll try g of b now. And g of b is going to be the integral from a to b of f of t dt. And again, you just kind of have to look at it and say, well, if I go from a to b, I'm going to have the same area I had before, this negative piece, that positive piece. Now we're going to dip back into negative territory here. So I'm going to lose some area, but then I get to make it up and I get to gain some more. So then overall, wouldn't you say that the area that I lose is not that much compared to the area that I've gained after D? So then if I consider the entire area from A to B, wouldn't this area be more than just A to D? Although remember, from A to D, we lost this area here. This was a negative number here. But then if I keep going all the way to B, I'm going to lose a little bit more of area. But then I'm going to gain more than I lost from D to E. So then what can we say about g of b? We can say this integral is greater than g of d. Do you follow my reasoning? Please think about this. Again, g of d was only the area from the net area from A to D. From A to D, I had a negative number here and then a positive number here, which was more than enough to compensate for g of A, which was exactly 0. But if I go A to B, then I'm going to have the same number that I had before, whatever this number was. I'm going to lose some of it, but then I'm going to gain it back and some extra amount, because the area from E to B, I can see clearly that it's more than the area from D to E. So then this statement must be true. Whatever area I get from A to B has to be greater than whatever area I got from A to B. And so now we can make a statement that says g of B is greater than g of D, and g of D was greater than g of A, and those are my two endpoints and my critical value. So then it must be that the absolute max is g of B. Okay, so I just resized what I had here on the screen, and so now based on what you see here, I can make the following statement. G of B is greater than G of D, that you can see right there as we discussed just now, and G of D was greater than G of A. So I'm going to continue making that statement. G of D is greater than G of A. And based on this compound inequality, now I can say, therefore, G attains an absolute maximum value of, now remember, the absolute maximum value, it's a y, so you have to say an absolute maximum value of G of B. And I guess we could say at x equals B, which is a little redundant because you did say G of B. So then this is how we evaluate absolute extrema, by locating the areas, and figuring out which of the critical values or endpoints gave you more area. Now let's answer the following question. What about the absolute minimum? So we're going to follow the same process. I'm going to start up here. I'm going to say for the absolute minimum, let's start by saying that G attains a relative minimum, or in this case relative minima, at x equals, what were they? C and E. And the justification for that is because G prime, which equals half, changed or changes from negative to positive at those points. Now it's the same thing we wrote earlier, but I'm assuming that that question was never asked. I'm just saying, what if the question was find the absolute extrema? Then you have to start this whole process. So first you have to tell them, hey, there's a relative minimum at this point, and you have to justify why that is an relative minimum. And now we can say, let's compare those two critical values and let's compare them to the endpoints as well, because none of the endpoints were an absolute max, so there's a chance that you could have one of the endpoints be the absolute min. So then what I'm going to do is, same as before, I'm going to try g of a, g of c, g of e, and g of b, and compare them all. Oh, wait a second. G of b was the absolute max, so I don't have to try b again, because that was the absolute maximum. So then we're just going to start with g of a, and we can say that g of a is equal to 0. You don't have to state why, you've already stated that before. Now I go to my first critical value, which is g of c. And so I'm going to go back to my function, and I'm going to use my function to figure out g of c. So that would be the integral from a to c of f of t dt. And what can you say about the integral from a to c? I can tell you that it is less than 0, because when you look at the area from a to c, it is below the x-axis. So then this is less than 0. So at this point, g of c is less than g of a, because g of a was actually just 0. So g of c is less than g of a. And keep in mind, we're looking for the absolute minimum. Now I need to compare c to e, because e was the other relative minimum. So now g of e is going to be the integral from a to e of f of t dt. And let's think about it. You're looking at it from a all the way to e, and you just looked at g of c. So g of c was this piece right here, which was negative. Now if I go all the way to e, I'm going to have some positive number here, because the area is above the x-axis, and then I'm going to get to subtract a little bit more. But this blue area here is considerably more than this negative area here. So then we can say that, hey, look, if I go from A all the way to E, will I have more net area than I had from A to C? Or will I have less net area? Will it be, I guess you could say, will it be more of a positive thing or more of a negative thing? Well, from A to C, you have a net negative number. But if you go all the way to E, this little negative piece, I think I can find a region here that compensates for that negative piece. And so then overall, there's more of the blue than the red after C, which will make the area from A to E a net gain of area. So then I hope you can follow what I'm saying when I say that G of E is actually greater than G of C. Because G of C was negative. G of C was negative, but it looks like G of E is, this blue area here is really going to give you some gain. And you do get to lose a little bit back, but this is too much for this piece. So this is a safe statement to make. And that is it. I don't have to try the other endpoint. Remember, my last endpoint is B, and I should always consider endpoints when I do absolute max or absolute min. But because B was the location of my absolute max, then I don't need to try it here. Okay? And so now we have a statement that says, this statement here says that G of C is less than G of E, right? Because if G of E is greater than G of C, then G of C has to be less than G of E. And G of C is also less than G of A. And it doesn't matter who the lowest one is between G of E and G of A, because G of C is lower than those two. And I'm looking for the absolute min, so I'm ready to make a statement. Therefore, G attains an absolute minimum value, by that I mean Y, the absolute minimum value of, and I have to give a Y, and the lowest Y was G of C, and this is very redundant, but it's going to be safe if I say at X equals C. So then, again, the idea is by looking at nothing but areas below and above, and keeping in mind if you have more area above the x-axis or below the x-axis, then you can actually compare critical values and endpoints and make a decision as to where you have an absolute max or where you have an absolute min. Don't forget, you have to start off with the relative extrema to explain why you are even considering these numbers. And so we made a case for the relative maximum, we made a case for the relative minimum, and then here we check just about everything, the relative max, along with both endpoints. And because one of the endpoints gave us the absolute max, then we don't have to check that endpoint again for the absolute min, because that would be a contradiction. And it's a lot of work, but trust me, you can do this, and you can do it in a fairly short amount of time if you know what you're doing. I can tell you that this will be on your AP exam. They really like these questions, and it tests quite a few concepts. And the thing they like about it is that they gave you no numbers whatsoever. On that number line, you only have A and a B and a C and a D and an E, and you really have to understand your calculus to be able to figure out the absolute max and the absolute min. Again, remember that on my last video, I gave you the homework assignment, and you should be able to do the ones that I've assigned. And I hope this video helps, and we'll have another discussion in class, but we'll also cover new material. So I'm expecting that you're able to finish most of the homework. Then we can answer a few questions from the homework in class on Monday, and maybe, hopefully, like I really do want to cover new material. All right, see ya.